Bonjour à tous, ici présents en personne, puis à ceux qui sont en ligne. Aujourd'hui, on est Québec-Océan et très heureux d'accueillir Sara Pedro, qui est écologiste marine. Sara a une formation en écotoxicologie et en réseau alimentaire marin. Sara s'intéresse aux impacts des facteurs de stress anthropogéniques comme les contaminants environnementaux et les changements climatiques et comment ils vont affecter les réseaux alimentaires. Sara est titulaire d'un doctorat de l'Université du Connecticut où elle a travaillé sur la manière dont la redistribution des espèces induites par le climat dans l'Arctique affecte l'exposition aux contaminants des mammifères marins. Son doctorat a été réalisé sous la supervision de Melissa McKinney. Actuellement, Sara est chercheure postdoctorale à l'Université Laval où elle travaille sous la supervision de Mélanie Lemire et Frédéric Maps et elle développe des modèles de réseaux alimentaires marins qui visent à soutenir la sécurité alimentaire des Inuits. Donc, sans plus attendre, Sara, je te laisse la parole.
Merci pour la présentation. Donc, je vais commencer. I'm going to switch to English. It's a bit easier for me. So in this presentation, I'm going to answer this question that is sort of the work I do. So how can food web models support food security in the North? And I'm going to start with a basic, just to make sure that we're all on the same page. What is a model? So in science, a model is defined as an incomplete physical, conceptual, or mathematical representation of a real phenomenon that is difficult to observe directly. So basically what this says is that we use models to try to understand complex stuff in the natural environment. So for example, something as simple as this is a model. This is a diagram of an algae with the different parts to try to understand how this system works. And marine ecosystem models try to understand the ecological interactions among species. So we define an ecosystem model as a model that describes the interactions between at least two ecosystem components that can be, for example, species or populations of different species. And the interactions are the real ecological processes. In this case, these processes are predation, so how the animals are connected through the way they eat. And we use this because there's a lot happening below the surface that we cannot observe. So why not building a model and try to understand what's going on? But species do not exist alone with their ecological interactions. There's other factors that influence food webs, and they can be environmental, ecological, or anthropogenic in the case here when we have a fisherman taking fish out of the ocean. So these factors can be ecological, and I was talking about the food web components and their relationships. There's different ecological processes. These include, for example, migration, species moving in and out of an ecosystem, competition, and then the predation or other processes like recycling of organic matter. Then there's the environmental component. This can be many things from vertical mixing in the water column, oxygen levels in the water, nutrient levels, the temperature of the water or the environment, salinity levels, and even light that affects many species, including, for example, the primary production. And then human factors, which are also many, starting with the one that is more obvious, like fisheries, can be commercial or for subsistence. But there's also lots of tourism activities that take place in the ocean and affect different species. There's ports and marinas, and even fisheries management and other management policies can affect the food web, as well as pollution like oil spills, for example. So why do we model marine ecosystems? So the very first reason is to understand the ecosystem, to take apart all the complexity of the system in different pieces and how these pieces interact with each other. Another reason why is to find out what we know and what we don't know about a certain ecosystem. So once we build a model of a food web, there's so much data that goes in it, and sometimes there are systems that are quite well known and there are systems that are not so very well known. And then we can define points that need to be studied in the future, for example. Another reason is to do forecasting and model scenarios. What does this mean? So basically, when we do forecasting, we are looking at how the food web might have changed in the past, and are these changes in the past related to environmental conditions like the weather, but also the productivity of the species, very natural changes in the abundances of different species. And then we can extrapolate into the future, also by using environmental variables and looking at how, based on how species change in the past, how they might change into the future. But we need to be careful here because models do not predict the future. We're not wizards here. All we're trying to do is to understand how changes may occur. So it's more of a way of exploring possible futures based on what we know about the ecosystem. And then this can inform decision-making. And this is widely used, for example, to evaluate alternative management strategies regarding fisheries, but also in conservation. For example, when we're delineating marine protected areas, and also in control of invasive species. And this is done by comparing multiple management options, and then we evaluate each option against a clearly defined objective that can be, for example, improving the sustainability of a fishery or minimizing a species probability of extinction. So to build a model, we go through a process that starts with collecting data or looking into what data has been collected so far. And this normally is from scientific knowledge, so data from scientific studies, but it can also be from used data, which is data from fisheries or tourism, so probably more on the government side and regulatory side of things. So data can come from many different sources and should, because building one of these ecosystems is quite complex. There's a whole lot of data that goes into it. But there's other kinds of knowledge also that we can use, like traditional ecological knowledge, also called indigenous knowledge or local knowledge, and community knowledge, which is basically knowledge that exists in the local area, the area we're trying to model. What do people know about this system in that area? And this can come from fishermen or other people that observe this system quite often and they understand it. And also this knowledge that in many times has been passed from generation to generation. And then we can start with building a conceptual model. And this is an example of a conceptual model of a food web done in the Irish Sea. So the fishermen were mapping out what they know about the relationships among the different species that they have observed over the years. And then we can do a step up to a qualitative model, which is basically adding some quantification of the relationships, but in a more qualitative way. So it could be, for example, a species eats a lot or a little of the different prey. And then we have the quantitative model that is a mathematical representation of the relationships, where we, in this case, are going to use equations that describe these relationships, so it's more precise. Modeling can and should be done with communities that depend on or are involved in management of local resources. So this is where the community knowledge and traditional ecological knowledge can come handy and really be involved in the process of modeling. So this we will call it the knowledge co-production, where scientific knowledge is brought together with the community knowledge. And then we do participatory modeling. So everybody that is involved in a certain project that involves ecosystem modeling can be part of the modeling process. And this can be done in many different ways, but a good way is to do conceptual models. So like understand what the community is worried about, and also how the community sees their own ecosystem, their own surroundings. What are the main components for them, the main species that they worry about, and also if they have observed how the different species are affected by change. So this can actually bring to the model a lot of information that many times science is not aware of. So the ECOPATH with ECOSIM modeling framework is one of the existent modeling tools we can use to quantitative ecosystem models, and is composed of two main components. One is ECOPATH, which allows us to create a static mass balance snapshot of the food web. What this means is going to give us the foundational relationships among species. And this is based on different parameters like biomass, which is basically abundance times weight for each of the different components of the food web, diet composition of each component, the production and consumption rates, ecotrophic efficiency, and catches. Catches is the fishery catches, so what's taken from fisheries. And ecotrophic efficiency, it's actually not possible to quantify in the wild. So normally is a model that outputs this parameter, and it indicates the proportion of the production of each of these components that is used within the system. And then ECOSIM is the component of the modeling tool that allows for dynamic simulations. So with ECOSIM, we can look at how species have changed in the past, how the biomass has changed in the past, or all the other parameters in ECOPATH. And it allows also to include environmental drivers, so we can look at how climate change have affected the system. And then we can create different scenarios of change and look at that into the future. So when I'm talking about the mass balance, what does mass balance mean? It just means that all energy that goes in to a system or a component of a system equals the energy that goes out. So it is in balance. So we can think about this ringed seal as an organism of its own small little system. So all the food that it consumes has to be used. And part of it is used in production, so production of biomass. And other parts are lost through catches, predation, net migration, other mortality that normally is natural mortality like old age, respiration, and unassimilated food, which is normally the loss through feces. And then we need all this information to each of the groups, the functional groups that we're including in the food web model. And then we're going to have an overall mass balance food web model. So a bit on the Arctic ecosystem. It's a particular ecosystem mainly due to the seasonality of it that is created by the cycles of sea ice in the winter and summer. Our main primary producers in this ecosystem are phytoplankton and sea ice algae. And there's species that are resident in the Arctic, meaning that they stay there year-round, like polar bear and ring seal. But there's other species that are seasonal, coming only in the summer when there's open water. And when we talk about Arctic, we talk about sea ice, obviously, in the marine environment is a very important component of the system. And the seasonality of it all occurs differently in different regions, but there's regions that are open water in the summer and completely frozen in the winter. So the primary production blooms occur only in the summer when there's enough light going through the water for primary production to grow. And this triggers a seasonality in all production in the whole food web. So this is one of the main reasons why climate change is affecting not only the physical part of the Arctic, but the biological part of it as well, because the sea ice is so important. So as the temperatures increases, we are losing sea ice. It's becoming less thick, and the extent of it is decreasing as well, while the open water season, the summer, is becoming longer and longer. And this affects the primary production, so the timing of it and the abundance of primary producers, which then can lead to mismatches with the zooplankton growth, which are the first level consumers. It can lead also to changes in local abundances, and this has been observed for species like Arctic cod that are becoming less abundant in some Arctic regions. And leads also to changes in habitat. For example, species with a more strict biological and physiological tolerances, like beluga whales, narwhal, and bowhead whales, are predicted to change their habitat range as the Arctic warms. And then there's changes in prey availability, because if the species are moving around, then the predators might have a harder time finding their usual prey. Also leads to more opportunities for species coming from more temperate regions, like some fish like capelin and sandlins are becoming more abundant in more subarctic regions, and they can then compete with other species like Arctic cod. And there's also greater prevalence of seasonally migrant species like killer whales that are now more abundant and seen for longer periods of time in the Arctic. And then because they are top predators, they can influence the whole food web from top down. And we cannot talk about the Arctic without talking about the people. Inuit have hunted local marine species for hundreds of years, including beluga, seals, narwhal, and fish like Arctic char, also bivalve. So many species are important for Inuit. And here you can see an example of some of their favorite meals. Here is beluga niku, which is air-dried meat, and beluga martak, which is a blubber and skin of beluga whale. And actually these foods are quite rich in nutrients and healthy fats. So they play a really important role in the nutrition and well-being of Inuit communities, not to talk about how important it is for their culture. Their harvest activities are a very important component of how they identify themselves. So the ongoing changes in the ecosystem are affecting the availability, the quality, and the accessibility of marine foods to Inuit, which are key pillars of their food security. Food security exists when all people have physical, social, and economic access to sufficient, safe, and nutritious food that meets their food preferences and dietary needs for an active and healthy life, according to the United Nations. However, indigenous peoples, particularly Inuit living in the north, experience really significant health inequities, especially in food security. They're up to 63% more food insecure relative to the 8% of the national average in Canada. And this is associated with very many factors. For example, the changes in sea ice, which affect hunting activities as traveling in the sea ice becomes more dangerous, as the sea ice is more unpredictable. the changes in species distributions, some Inuit report that is some of their usual hunting activities have to take place further away from the community than before because they have trouble finding the animals. The cost of food and harvest, it is expensive for many families to go hunting because the vehicles might be expensive, the fuel, the ammunition, there's a lot of materials that go into it. But on the other hand, the cost of food in the supermarket is also not low and doesn't offer a very easy option to their hunting practices. I've seen on my visits in the north, chickens at $40. So if you pay $40 for a chicken, obviously it's hard to feed the whole family. And then health and nutrition, as hunting becomes, there's a lot that goes to it. There's also the cultural aspect and the colonization that affects their diet. So there has been a change from a more diet based on country foods, so the local marine foods, to a diet with a bit more foods from the supermarket. But these foods are not always the healthy ones. And so this diet change is associated with an increase in chronic disease among Inuit as well. So now that I gave a background into all of these concepts, I'm going to talk a little bit about the work I'm doing and how we're using these ecosystem models to address food security. So I'm working in these two big projects. One of them is in NUNAVUT, where I'm modeling the West Baffin Bay ecosystem, which you can see in blue in this map. This is a project from IOPAR and CIHR that was awarded to Melanie Lemire and Laurie Chan and other collaborators. And then this big project in NUNAVIK that has just been funded by Sentinel North, and we're just starting now, to Fred Mapps and Tiffany Kenny. And here we're going to model the marine ecosystems of Eastern Hudson Bay, Hudson Strait, and Ungava Bay. So in NUNAVUT, ecosystem model of West Baffin Bay, our objectives with this project are to understand the food web structure and function of Western Baffin Bay coast and shelf ecosystem, and then to link the ecosystem change with nutrition and health data. This is done with the community of Rikiktajuak. And then co-develop food security scenarios with the community to address ecosystem change and Inuit food security issues. So a bit on our framework, just to give you an overview. I just finished building this big ecosystem model for the West Baffin Bay, and is based on data sets from the literature and also from collaboration with many people. Then we hope to integrate traditional ecological knowledge through interviews with the community members, especially the hunters. And we have data from 3 major studies on diet, nutrition, and health in Rikiktajuak, and this is led by our food security experts in the group, led by Professor Tiffany Kenny right now. And there's data from 3 points in the past, in the late 90s, the late 80s, the late 90s, and the late 2000s, and hopefully we'll do an updated one. And with this data, we can look at how nutrition and the diet has changed over the years. And then through workshops, we're going to gather information from traditional ecological knowledge, the diet health models, and the community concerns. And all of these can then inform also the ecosystem model to address food availability in the area. So the model can tell us how much of each species is in the area. And then with the community during the workshops and with all this information, both from the models, the ecological models and the diet health models, we can co-construct scenarios and adaptation strategies regarding food security using the ECOSIM tool. So on the first objective, the food web structure and function in Western Baffin Bay, I'm going to show some of the results of this objective, which is how far we've gone with this project. So I updated a food web model existent for this area from Janjua that is published from the Department of Fisheries and Oceans. And this model has a total area of 81,450 square kilometers, and it represents the years of 2011 to 2016. And this area was selected this way because it encompasses the ecologically and biologically significant areas called Baffin Bay Coastline and Baffin Bay Shelf Break, defined by the Department of Fisheries and Oceans. And they define these areas because the Baffin Bay fjords and this coastal shelf are very important for various marine mammal and seabird species, and also fish, as the species reproduce or feed in these areas or migrate through. In this area, there's a lot of subsistence harvest going on from the communities of Riquitajuac and also Clyde River up north. So this area is important for the Inuit. And there's also a commercial fishery for Greenland halibut that is Inuit-led. The model has 30 functional groups, among which are marine mammals and seabirds. And the species that are not included in the functional group, that are single species groups, are those that I found were more important for the community. There's fish and large invertebrate groups, zooplankton groups, benthos, and primary producers and detritus. The functional groups were defined based on common traits of different species like diet, trophic level, and habitat use. And the reason why we group some of the species instead of trying to model every single species that exists in this area is to simplify a bit, because adding complexity to the model, especially when we don't know a lot about a lot of these species, would just increase the uncertainty in the model development and outputs. So back to here, you can see that in yellow are some of the seasonal species, meaning that the species come up to Baffin Bay only in the summer when there's open water. In the purple, you see the species that are important for subsistence harvest for the communities. And in green, the species that is of commercial interest, the Greenland halibut. So here is a representation of the system as an output of the ECOPATH model. You can see the circles represent each of the species or functional groups defined, and their sizes represent the relative abundances. So the bigger ones means that they're more abundant or they're larger biomass than the smaller ones. And the links between them represent their feeding relationships, with the thicker links representing those species that are the preferred prey of a certain predator. And the trophic levels range from 1 to 5. You can see at trophic level 5 in green, we have only polar bear and killer whale, with our killer whales, which are our top predators here. And in yellow are the primary producers, and the other groups are in between. Marine mammals normally occupy either trophic level 4 or trophic level 3, besides killer whales and polar bears. This figure, I wanted to show you just to have an idea of which components of the food web are more important controlling the whole system. So you can see here in the positive part of the graph are the species that control the system. So that means that their biomasses are more important affecting the other species. And in the negative side, you see the species that are more controlled by the other components of the food web. So killer whales and polar bears are quite negative, which means that their biomasses are controlled by the system. Whereas here it's mostly all other groups And you see cephalopods, other marine mammals like narwhal, bowhead whale, ringed seal, and walrus are quite strong controlling the system. And then among fish, Arctic cod is the one that has the highest control over the system. So this indicates that species at intermediate trophic levels are controlling the system, what we would call a bottom-up controlled system. Here we can look at this a bit more closely. In darker purple, we can see a stronger relationship. So this graph tells us the relationships on one-on-one, so how each species or functional group directly relates to each other. And you can see that killer whales are highly controlled by narwhal and bowhead whale and other prey, and polar bears are highly controlled by ringed seal. And this explains why they have negative overall control. It's because they are highly controlled by their prey in the system. But another thing this graph tells us is that there is not a whole lot of really strong links between species, which we can probably assume that means that species are sort of flexible. They're not fully dependent on the one prey. Rather, they might be feeding on several different species, and maybe they're flexible in changing their diets if there's some sort of perturbation to this system. So, conclusions of this work, of this objective, this first objective of this work, we have a model of the West Baffin Bay ecosystem. And this model is just foundational information of what we know about the system from scientific knowledge. And it also provided information on the knowledge gaps and uncertainties still associated with it. I haven't gone through much into it, but just as an example, I had a hard time finding data on the abundance and diet composition of fish, of most fish groups and benthic groups in the model area. And the ecology of important species like ringed seal, walrus, and Arctic char that are very important for Inuit is poorly documented. So we don't know a lot of their migration routes, how much time they spend in the model area, and in some cases even abundances and diet composition. So there's still a whole lot to know about this system. And due to that, there's certainly a lot of uncertainty associated with this model, but it's a start. And then with working with the Inuit partners in Riquitajuac can actually help quite a lot improving the model. We're hoping that through the interviews and the workshops, we can have more information about this system and discuss more with our partners about their concerns and how what are the main drivers and the main components of this system. And then we can improve the model, and then we can move to the other steps of creating together different scenarios based on climate change and based on the concerns of the community on how the species biomass might change over time. And then based on that and the results from the diet and health models, we can brainstorm adaptation strategies. Unfortunately, these objectives of this project have been delayed quite a bit because it hasn't so far been safe to travel up north. So we're hoping that soon we can move on with this. So now for the NUNAVIK project, this is quite a new project. We got funded recently, so we're still in the process of starting the whole thing. And the objectives are to assess the availability and quality of key aquatic species in NUNAVIK, then link this ecological part of food security to the economic, social, and cultural components, to be able then to co-develop food security scenarios to address ecosystem change and Inuit food security issues similar to what we're doing in NUNAVUT. One particularity of this project is that we base all our objectives on data that already exists, so we don't have to collect new data, because there's so many projects that are ongoing or have been done in NUNAVIK that can be used to build these ecosystem models and to address food security. For example, the BRIGHT project, also from Sentinel North, estimated, reported levels of contaminants and nutrients in several species that are important for Inuit in the region. And there's other projects that are ongoing, like Fishies project, that is a new one that is trying to integrate genomics and fishery science with indigenous knowledge, and then address socioeconomic challenges and opportunities that are related to food security. So more focus on fisheries. Then there's a model that was already built for Eastern Hudson Bay that we can update and work on by Hoover in 2013. And to add a bit of the terrestrial component, we have collaborators from Caribou Ungava project that have done models of population dynamic of caribou in the area. And the Hanui Lirpita health surveys gathered a lot of data on social, cultural, mental health and wellness in NUNAVIK. This is a large-scale survey that was done in 2017, following another one that was done in 2004. And there's other projects and collaborators that are involved in this big project. So here we propose to model the Eastern Hudson Bay, Hudson Strait, and Ungava Bay areas, so 3 different ecosystem models, because these areas have different oceanography. And the first objective can be translated into this one big question: how much food is there, and how nutritious is it? So we'll answer this question with the marine food web models for the different regions. But in this case, we also want to try to model the dynamics of fish populations that are anadromous, meaning the fish that live a part of the year, a part of their life cycles in the ocean and another in the rivers, and try to connect this to the marine food web models. Regarding quality of food, aquatic ecosystems, as we know, are the main food sources of high quality nutrients like essential fatty acids. So we want to model how these essential fatty acids move in marine food webs to better understand also how they might be affected by climate change in different scenarios. And some of our collaborators, as I mentioned, are developing population models for caribou, which brings a terrestrial component into this big project. The second objective can be translated into how accessible is the food. And this is the part where other components of food security come into play. So here we'll try to bridge the economic and health components of food security to get ecological component, that is the changes in species availability and quality that we can take from the ecosystem models. We can answer questions like, what are the economic costs behind traditional harvest to an Inuit family or community? And how does it compare to the costs of healthy foods and local markets? And then what are the dietary, nutritional, and food security implications of changing ecosystems and country food harvest in NUNAVIK? And this is our food security experts in the group, of which I'm not part of, that have very well-defined methods that allow to design diets that respect cultural food consumption patterns, nutritional requirements of healthy persons, and that are based on local resources, ecologically sustainable and economically attainable. So it's trying to create diets that will be respecting all of these components of food security as best as possible. And then the last objective, will there be enough food in the future and how can we adapt? This is the part where we do the development of modeling and analyze the results and project scenarios together with the community. So what do Inuit think of the future Arctic ecosystems and their food security, and what role will environmental and societal factors play in changing country food consumption? So through workshops and also maybe by building conceptual models, we can understand what are the concerns of the community and the communities and how they see the changes that are occurring. And then how would the communities like to respond to the projected changes in country food supply, marine and also the caribou and aquatic, to ensure the food security over the long term? And will there be opportunities for alternative local foods to complement the traditional harvest? So this is where it's important to co-construct these strategies, because there's so many factors that affect food security that are more of a human dimension. Okay, so if you don't have already the answer to the question, how can food web models support food security in the North, from what I've just talked about, I'm just going to give you a wrap up of it. First of all, we can understand how species interactions affect food availability. So by building a model of a food web, we can understand which species are there, what roles they play, and then we can do a look at how environment is affecting the abundance of different species, and then how they're going to be available for Inuit. So it puts the role of the local ecosystem into the big picture of food security. Then we can do scenario development and analysis with the communities. So use the models and the fact that we can look at possible future scenarios and analyze them with the communities to better inform how they want to adapt into the future, to think about different alternative foods, for example, or hunting strategies, or in general, what kind of diet they would want to have and would be ideal for their needs. That's it. And if you have questions, I'll be very happy to answer.
Nous avons une question de Maxime Benoît Gagné à tout le monde. Je vais te laisser, si tu pouvais la lire dans le chat, s'il te plaît.
Do the adaptation scenarios include the possibility to incite the Inuits to start eating new local species? What is the reception? That's a good question. And we haven't really had the opportunity to go further in the process of consultations and workshops with the communities. But I think it can, but I think it has to come from them, since I mean, from a personal point of view, what I eat is really personal and is really cultural, and I think a lot of you in the audience probably feel the same. So sometimes, not sometimes, but all the time, it's important to be able to make our own choices. They are based not only on how much we can afford the new food, but how does that food come to our plate, and how can I cook it? Do I know how to cook it? So there's a lot of things that go into it. And honestly, as an example, in Requitajuac, there's a commercial fisheries for Greenland halibut, which is quite appreciated in many countries as a food, and I think it can be quite expensive sometimes. But in Requitajuac, people didn't want to eat it. They were giving it to the dogs. It's not part of what they ate, so they didn't care about it. So yeah, I think it really depends on them. But it's maybe the models and the results from this project will be a way to show them that there are other options out there.
Merci. Nous avons une autre question dans le chat de Kashish Miranda.
Kashish says, I enjoy the community-based approach. What does integrating indigenous traditional knowledge into a numerical mechanistic model look like? This is also a great question. I'm still exploring this part. But for example, this work has been done in different parts of the world, so I know it is possible. But since I haven't done it myself, I cannot give you a very precise answer. But this kind of indigenous traditional knowledge can, for example, let's say I have articod as the main food for 3 different predators. But then I consult the communities and they tell me that actually there's a 4th predator that eats articod that I'm not aware of. Or there's let's say, I'm not considering all the species that I should be considering in my model. Let's say I forgot one that I thought didn't exist in the area, but actually is quite important and they've seen it very often. So these are ways in which we can include it. And if I'm not aware, if I don't know exactly what numbers to put, we can sort of merge qualitative with quantitative. So I can ask the community, is it okay, so articod is important for this other predator, but how important is it from, I don't know, would you tell me, is it high, low, or medium importance? And then I can sort of do an approximation, a numerical approximation of what that looks like.
That's great. Thank you.
Thanks.
Hi, Sara. Thank you for your talk. I was wondering, once you finalize these models, and I know they're never-ending stories of models, but when you go back to the communities with those models, how would you plan to communicate them? Can we communicate the results of the models with the community?
Yeah, so for now, what I was thinking about doing is bringing the model, but starting with just the conceptual model of it, instead of like showing funky numbers and stuff. So having a conceptual model and discussing it with the communities. Do you agree with these relationships? Is there something missing? What do you think about it? So maybe just use diagrams and simple things, at least for the part of ECOPATH. For the scenarios, I think first to probably create them with the communities. And then we can look at graphs and other kinds of outputs of it. So I'm not 100% sure yet, but I visualize it as a very, as a meeting, like based on graphs and diagrams that we can build together and discuss together. Does that answer your question?
Yeah, I think there's no right question to this. I'm still searching for an answer. So
yeah, I know there's lots of different methods that have been used in this kind of project, but I haven't explored all of them yet, I think. So, well, we're in standby to when can we actually go to the community and have these meetings.
Okay, thank you.
Oui. Thank you, Sara, for the presentation. I was wondering, for the West Baffin Bay model, what were the main sources of data that you found for describing the food web structure?
What are the main sources?
Yeah.
Well, for this, we only have scientific sources for this model, but mostly is, well, a lot of it was work from Department of Fisheries and Oceans to report some species abundances in the area. But there's some scientific literature that also reports abundances. Diet composition all comes from scientific literature of species diet composition in the area, but some of the data that I used was actually not taken from the area, or is more qualitative when I couldn't find data for species. And as I mentioned, that's a lot that we still need to know. But those are the main sources, I would say.
Were there trophic levels where you found that the information was especially scarce?
Yeah, for fish, we don't know the abundance of most fish species in the area. I know there's some surveys from the NAFO, the North Atlantic Fisheries Organization, with the Department of Fisheries and Oceans of Canada that has been taken for a few years along with the Greenland halibut surveys that has been done because of the commercial fisheries. But this data is not quite analyzed, is not ready to put in a model. So yeah, so there's some data, it's a bit sparse, but I would say fish is a big hole in the system, and then benthic species, it's we don't know much about benthos. Unfortunately, it's still a big hole on data as well. Or sometimes the data is quite old, like for seabirds, for example, the abundances are from the 70s, and we don't have estimates that are recent. So there's a lot.
Thank you.
Une question dans le chat de Connie Marja.
The definition of detritus is always a bit weird, unless it is a very coastal region. Where does your detritus box come from? So my detritus, I calculated it based on data from the Green Edge project. There was a big project done in on board of the Amundsen, I think. And he measured some of the detritus. But then for the cycling of it, the detritus end up being the unassimilated food as well from each species. It's not the most precise because when we do these big food web models, we cannot be really precise on anything. It's like it ends up being a more broader perspective.
Je pense qu'on a une question peut-être de Brigitte Robineau.
Yeah, I was wondering if it would be interesting to adapt your model or to change your model to integrate this model with the data coming from fish larvae, for example, to check if the relationship with the phytoplankton would be strong or not. Because I was surprised that phytoplankton is so weak in your model.
What do you mean weak? He has a small abundance?
Relationships in your diagram, phytoplankton doesn't appear, doesn't show a strong relationship, for example, with copepods or with
I understand.
fishes.
Yeah, so you say double check with data from what?
From fish larvae, for example.
Okay, no, I'm not entirely sure, but I think one of the reasons is it's because maybe there's zooplankton, especially the copepods, feed mainly on phytoplankton and sea ice algae. So they do have a strong relationship in terms of dietary composition. But what can be happening, though, we don't see that limitation in the system control, is that we have enough production of phytoplankton to satisfy the abundance of copepods in the system. So I think for killer whales and polar bears, it happens that they are more constrained by their prey because they also have a smaller biomass in the model, or their prey have a smaller biomass. So if that prey is missing out, it's a bit harder for them to feed. So yeah, we have to analyze a bit deeply.
It has been shown that fish larvae, for example, are constrained a lot by their food, that is phytoplankton or copepods.
Yeah, it can be related also to the more coarse nature of a whole food web model. We probably see those more tight relationships when we're looking at just a little part of the food web. But then we're looking at everything, and because maybe in some cases the data is not as precise, it can mask some of these important relationships as well.
Thank you.
Moi, j'aurais une petite question, Sarah. Est-ce que tes modèles intègrent des des incertitudes dans tes données, parce que des fois, on peut avoir tout dépendant d'où on prend nos données, on peut avoir certaines incertitudes quant à l'identification.
Yeah, it can include uncertainty. The model can include uncertainty levels. But I haven't talked too much about it because I was just showing the basic food web and how it's connected. Normally for models built in ECOPATH, where we see the effects of uncertainty is more when we're producing other outputs. Like if we're doing model scenarios, we can look at how the species are changing over time and within certain confidence intervals defined within the model. Or if there's other model outputs like network analysis. There was some uncertainty in one of the graphs that I showed that had the bars, that shows like how based on the uncertainty in input parameters were affecting this output of the model part of the analysis. So yes, ECOPATH integrates uncertainty, but many times in these big modeling frameworks, like, well, this is particular of the software ECOPATH, we tend to include uncertainty levels around each parameter that are more based on qualitative information. So let's say a model, we give it more uncertainty when the data is not collected in the region, and is or when the highest level of uncertainty is when the model is in itself estimating a parameter that we don't have data for, and then the less uncertainty is given to data that was collected in the area with very precise methods. So it's more of a qualitative way of including uncertainty for ECOPATH.
Thanks a lot, Sarah.
Thank you.
Merci beaucoup d'avoir présenté ton travail. Je vous donne rendez-vous le 23 novembre pour notre prochain webinaire Québec-Océan. On accueillera une autre stagiaire doctorale, Tessa Page, qui nous parlera des coraux et des changements climatiques. Donc, merci beaucoup.
Merci. Thank you.